The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right. Morning, everyone. I hope you all had a great spring break, and during which I hope you can have more of 6046. Today, we're going to look at network flow and two things in network flow. The first one is Edmonds CARP algorithm. And after that, we're going to look at two applications. And in particular, they are called bipartite matching and cover. Okay, so we'll start with a simpler algorithm, which is Ford-Fulkerson. Can someone remind us what Fulkerson does? Go ahead.
Every time you have an augmenting plot, it gets rid of it.
It gets rid of it? Yep. What's your name, by the way? Misha. Okay, so, well, Misha gave a very brief description, but let's be a little bit more detailed. So we have a graph network flow, G, and the first thing it's going to do is that given the flow, it will transform G from a residue graph. Right, everyone remembers that? Then FF algorithm will find the path going from source to sink in this residue graph, and then augment this path. Augmenting just means increasing the flow on that path. By how much? Go ahead. Yeah, the minimum edge on the path. Let me just define that to be the capacity of the path, which is the capacity of the weakest link. Okay, then what's the last step we're missing here? So after augmenting, our flow changed from F to F prime. And then we're going to loop back. Right? We have a F prime, then GF prime, find the path in GF prime, and continue from there. So this algorithm, in some sense, is not even a very detailed algorithm because it doesn't say how to find a path in the second step. And that's indeed a problem because we have seen a pathologically bad case where each capacity is a billion, and the correct way to do it is simply like augmenting this path and then that path. Oh, sorry, there's an edge 1. Right. Then we'll be done, but the pathologically bad case is we keep going through this middle edge. Okay, so Edmonds CARP is an improvement to this algorithm. Let me just write it here. Its first step, third, and fourth steps are actually exactly the same, no change from Ford-Fulkerson. The only thing it does is that it finds a special path. Did Srini cover this in the lecture? That what path Edmonds-Karp finds? I see some people nodding. Okay, go ahead.
You run the breadth first search from the source to the sink in GF, take the shortest path.
Okay, does everyone agree with that? So Edmond-Karp finds the shortest path from, I guess, can you see that part? Nope, oh, sorry about that. Find the shortest path. Here, shortest just means least number of hops. Here, in this pathologically bad example, Edmond-Karp will do much better because it will find this path instead of this weird path, right? Because that path its distance is 2, and the one going across the middle is 3. Okay, now we are going to prove that this algorithm runs in order VE square. So okay, so one step back. Do we have to prove that it's correct? That it indeed finds the maximum flow. Yeah, I claim I don't have to do that because it's the same thing as fault focusing. Right? You can find any path. Now, we want to bound this runtime. So any idea, high-level idea how we are going to do that? In which several steps? Okay, so okay, a simpler question. What's the complexity of this second step? Find the shortest path from source to sink. Go ahead.
OV plus E.
OV plus E. And in this case, actually, V is always less than E, right? So I can simply say O of E. Now, how long does it take to augment that path if we have found it? O of E. That's correct. But I claim we can also say it's O of V, right? Because the shortest path at most has V hops. And then from F to F prime, okay, so I think in some sense these two are the same steps, and also of V, and then updating the residue graph is also of V. So one of these iteration, each iteration takes how long? O of E, right? This is the most expensive step in one iteration. Okay, so what else do we have to do to prove this bound? We need to show that the number of iterations is O of V times E. Right? If we can show that, then we are pretty much done. Okay? Okay, now to prove that bound, we first need a lemma, which we call monotonic. So let me define delta F V. This is the length of the shortest path from S, from the source to V, which is a node in the graph, the length of that in residue graph of F. Okay, is that definition clear? And this lemma says delta FV for any vertex V does not decrease. Okay, so it can only monotonically increases. Okay, we're going to prove that. So we'll prove by contradiction. Assume this is not the case. That means there is some V that in F prime, which is the new residue graph, its shortest path from the source in the new residue graph is less than the old one. Right? That's we're going to derive a contradiction to that. But so there may be many such vertices that drop. But if there is any, I'm going to define V to be the one with smallest delta in F prime. Okay, any questions about this step? So there could be like V1, V2, V3 that all make this happen. So I'm going to choose the one among those that has the smallest distance from the source. Okay. Now here is my source. We have a path to V in graph GF prime. Okay, so this is a path. Then I can always find the predecessor, which I'll call U here. Okay, if this is the shortest path to V, what can I say about delta of V and delta of U? What can I say about these two quantities?
Can we decrease?
Mm-hmm.
Can we decrease one of them? Please?
This one is greater than that?
One of them must be.
One of them is greater than the other? And that's always true, right? For any two quantities. Okay.
U is U plus 1.
Okay. Misha said V is U plus 1. Does that make sense to everyone? Because that's the shortest path to V. It goes through U. Okay, that's correct. So, maybe I wasn't clear about that. I defined U to be V's predecessor on the shortest path. Okay. Then definitely delta F prime of V is delta F prime U plus 1. Okay. Now I'll use U to be my stepstone back to the original graph f. Right? I want to say something about this quantity and delta u in graph f. What can I say about that? This is a tricky part.
It's greater than the
This one is greater than that? Or the entire thing is greater than that? Okay, I'm going to claim this one is greater than delta fu plus 1, by which I'm claiming this quantity is larger than that. Can anyone give a reason why I can claim that? So recall how I defined V.
Can you repeat how you define V?
Good question. So V, so there are probably several V's that have delta f prime less than delta f. Right? I'm going to define V to be the one with smallest delta f, okay, among all those nodes that have a drop in delta f, in delta. Okay, this is probably a tricky part. Then by definition, since delta fu is less than delta f v, right? And I defined v to be the one with the smallest delta that satisfies that. So all the u's, so u is a predecessor of v, so u shouldn't be one of those nodes that have a drop in delta. Okay? So I know this is probably a tricky part, and yeah, I'll stop for questions, and yeah, make sure we resolve this part before we move on. How many people get it? Okay, only 2. That's not good. Okay.
I'm confused about how V can be the one with the smallest delta f if we have a predecessor with a smaller delta f.
Okay, so okay, maybe V to be the smallest, the one with smallest f, such that delta f prime is less than delta f. Okay. Okay. Maybe yeah. That's why yeah, I confused you guys. Yeah. Sorry about that. So we have a bunch of nodes who have a drop in delta, and I define V to be the one among them that has the smallest delta f prime. Question?
Sorry, I'm lost to what delta f prime is versus delta f.
Okay. Delta f of a node is the shortest path from source to that node in G of f, which is the residue graph given a flow, right? So f is, well, some flow, and f prime is the flow after we augmenting a certain path. Right? So f prime is one step after f. Okay, how many people get that now? Okay, still not everyone? Any questions about that? How many people like still haven't got that? Okay, so some people, it's like Schrodinger's cat. It's in the middle state. Well, then I'll have to move on, and I'll assume you all get this. Get that one. Now, as the last step, so of course we will ask, what's the relation between this guy and delta f of v? Right, because in the end we want to show a contradiction that delta f v is probably greater or equal to delta f of v. This is another tricky part. So let me ask maybe a simpler question now. So that is our g of f prime. So we also have g of f. Right? It has the source, some u here, v there, sink there. Does this edge exist in this graph? So I know that edge exists because I defined u to be the predecessor of v. Right? But uv is in that graph doesn't necessarily mean uv is in the old graph. So it could certainly exist, but is it possible that this edge didn't exist? How many people would say that edge definitely exists? How many people would say maybe it doesn't exist? Okay, it doesn't matter because we can prove both cases. So let's say case 1, uv is indeed in the original graph, g of f. Okay. In that case, can I say something about that last step? Greater or equal to delta v. Okay, why is that?
Because v was on the shortest path. Yeah, so the shortest path either passed through. Yeah, the shortest path from v either passed through u or didn't.
Correct. Does everyone get that? So the shortest path in this graph to v is not necessarily this one, right? But if it's some other one, okay, so in case 1, I'm assuming this edge exists, right? Then no matter what the shortest path is, it's definitely shorter than I first go to from S to U and then U to V, right? The shortest path between S to V is definitely shorter than I first go from S to U and then U to V. Make sense? Okay, so case 1, done. It's a contradiction because we showed that delta f prime of v is greater or equal to delta f of v. Any questions about that? Okay, case 2, uv is not in GF. Okay, so how can that even happen? Is it possible that this edge didn't exist?
It could be a like backwards facing edge that you add because the edge is full.
Okay, great point. That's exactly right. So it is possible that this edge didn't exist, but only appeared after we go from f to f prime. How can that happen? That must mean we are augmenting a path that goes right through it, right? But this edge doesn't exist, so we cannot be augmenting a path that crosses this way. We must be augmenting a path that goes like that, right? First from S to V, and then V to U, and then U to T. If we are augmenting such a path, then we're going to remove this edge from V to U, but we will add U to V to the next graph. Okay. Did everyone get that? So now here, more formally, I'm going to claim if we assume UV is not in GFF, and we also know UV is in GF prime. What does that mean? These two can only be caused by the fact that UV is in GFF, G of F. Not only in that graph, it must be on the path we are augmenting. Make sense? Okay, so given that, can we say something about delta F of U and delta F of V? So here is our P, right? This entire thing here. And P is the augmenting path.
U is delta P plus 1.
Correct? Right? So if that is the augmenting path, in Edmond Karp, we are looking for the shortest path, right? So V is the predecessor of U, then delta of U is delta of V plus 1. That means that quantity here is delta F of V plus 2. Okay? So it's also a contradiction to what we assumed. Okay, so that proves our lemma of every node's delta monotonically increases. Now here I'm going to show that our final theorem that we have at most VE number of iterations. So the way we're going to show that is we are going to define a capacity of the path. It must be the capacity of its weakest link. We are going to define its weakest link is UV. Okay, and we are going to show that UV, we'll call that critical edge. We're going to show UV can be critical only of V times. If that holds for every edge, then I claim all the edges combined can only be augmented of VE times. Now, how do we show that? So again, let's assume we are augmenting a path from that goes through U to V. If we do that, by our algorithm, we will get rid of this path, right, and have an edge backwards when we go from f to some other f prime. Now, when can I augment uv again? It can only happen if at some point I come back to augment the path going from v to u, right? And because that will eliminate this back edge and adds back our edge uv. Okay, let's see what happens there. Now I'll call this graph f, this graph f prime. So in f prime, we know we are augmenting the path from v to u by the same argument. Delta u is delta v plus 1 in f prime. Correct? And we know this one doesn't drop. Right? So it's greater or equal than delta f of v plus 1. Okay? And we also know in f, v is the predecessor of u. So this one is equal to delta f of u plus 2. What does that mean? It means in between 2 times uv is augmented, delta of u must increase by at least 2. Then how large can delta of a certain node possibly be? It's definitely bounded by of v, right? Bounded by v. So then I claim this particular edge uv can only be critical edge of v times, actually half of v times, strictly. So then every edge combined, there can only be half of v times e number of augmentation. Okay, any questions about that part, about the entire proof? If not, we'll move on. Okay, this is not part of the required in the recitation, but I'll quickly say a few words about an even better algorithm, DNIC, which runs in of v square times e. So this is an improvement to Edmond-Karp, and its idea is that I'm going to find all the shortest path in one go from S to T. Okay, I'm going to augment all of them at the same time. Then, because they are all shortest path, when I augment that, each path will be broken. Right? Maybe I'll get rid of this edge, and that edge. And the thesis is that the shortest path will increase. Right? Here, the shortest path is 3, but I have destroyed all the shortest path of length 3, so I'm going to shortest path of 4. If they do that, you can bound the number of iterations to O of v, because your shortest path can be at most v. But each iteration is slightly more complicated because you need to find all the shortest path, and it happens that they can show you can find it in v times e. That gives the v square of e. Okay, that's not the important part. And the more interesting part is that actually the author of this algorithm, his name is Dinitz. But his algorithm is very hard to understand that, well, nobody yeah, nobody got that. And there's some other guy whose name is, I think is Ivan. He understood the problem and started advertising to people and giving lectures on Dinitz's algorithm. So he popularized the algorithm, but unfortunately he got the name of the author wrong. And so that's why this algorithm is henceforth called Dinitz's algorithm. This is useful to know. Why? Because you can tell this story to other people, so they will assume that you know a lot about Dinitz's algorithm. Well, in fact, you probably don't, and that's exactly what I'm doing here. Right? OK. Now let's look at one application. Bipartite matching. OK, so the problem is that we have like several person and several tasks. Let me get rid of the one person because I don't want to draw that many stuff. So we have a graph like that. And each edge, if there is an edge, that means this person is capable of performing that task. And the problem is that find the matching, which means the assignment from people to tasks, such that we get as many tasks done as possible. Okay, so one person can only do one task, and one task only needs one person. So here you can see a bad matching, which is I assign this first guy to task 1, then no one can do task 2. Right? So if I'm smarter, I'll assign one of these guys to that task and have this person handle the other task. Is the problem clear? So this is called bipartite graph because, well, which means you can partition a graph into 2 parts. And within each part, there is no edge connecting any pair of vertices. And you can also define this problem for a general graph. The goal is the same, that find a subset of edges such that no 2 edges are connected to the same vertex. Okay, but we are going to look at bipartite graph. And we claim in bipartite graph, this can be solved using max flow. Okay, I'll give you 1 minute to think about that, how to transform that problem to a max flow problem. Any ideas? Okay, a hint. I will add a source here and a sink there. now have created these edges. Okay, how do I restrict the capacity of all the edges such that I can guarantee no person is taking 2 tasks and no task is assigned to 2 people? Make all of them weight 1. Okay, if we do that, 1, 1, 1, 1, 1, and everything here is weight 1, then that's definitely correct. What's your name? Calvin. Okay. If we do that, then, well, because each person only has 1 incoming edge. Oh, sorry, maybe I should have drawn the arrows here. Each person only has 1 incoming edge, so it cannot take care of 2 tasks at the same time. Right? Same thing for each task. It only has 1 outgoing edge, so it cannot be taken care of by multiple people. Okay, so if the max flow is k, that means we can find that the max matching is also k. And we can get k tasks done. It's very easy to see because we can have a cut here. And if the max flow is k, that clearly k tasks are taken care of. Okay, any question about that?
So the question is, can we do all these simultaneously?
Find an assignment from people to task to get as many tasks done as possible. So how many tasks can we handle? Okay, so I'm doing a different topic from the recitation note. In the recitation note, we are considering another problem called bipartite cover, which is exactly the same thing as that. So cover, also bipartite graph, is defined to as, let's find several vertices in this graph such that each node at least, okay, let me color several nodes in this graph such that each edge is connected to at least 1 dark node. Okay. And the nodes I colored is called a cover. I want to find the minimum cover. Right? You can, of course, you can of course cover all the nodes. That's trivially holds, but we are looking for the minimum cover. And the claim is that mean cover is k if and only if max flow, max matching is k. Why is that? Because in that matching, if we have a matching, then we have a set of disjoint edges, right? No 2 edges are connecting to the same node. So if we want to cover these edges, we at least have to add one of these guys, right? Color one of these 2 and one of these 2, right? So if we have k matching edges, then we at least need k nodes to cover them. For example, I can cover them like that. But this is not a full proof because I also need to show I can indeed find a cover that is k. Okay, let me think about whether I should prove that. Okay, I'm going to give it a try. If you don't get that, that's fine. Okay, cover is a set of nodes such that every edge in the graph is connected to at least one of the nodes in the cover. Okay, so this is not a cover because this edge is not covered. All right, so in this case, I probably have to add that as well. But clearly, there is a better cover, even a smaller cover, which is those two. Right? Yeah. So how are we going to transform that matching to cover? So let me first give a matching here. One max matching should be something like this. I have this edge and one of those two. That is a matching, right? That is a max matching. No question about that, right? So let me get rid of all these. One way to transform this into a cover is that I will first color these two guys. I'll color the nodes on the left where they are connected to a matching edge. Right? After that, I'm going to start from this one and jump between nodes, taking alternating path, meaning I'll take a unmatched edge and then take a matched edge and then take an unmatched edge again, but there's no such thing. Okay, and if I take this jump, I will swap them, make that dark. Okay, this graph is a little strange. Okay. Now I claim this is a cover. Is that? Yeah, that is one, right? And if there is another like unmatched edge going out, then I'll keep taking that alternating path. But I have to stop because there's no such edge anymore. How can I say, why can I prove, why can I claim this is a cover? So clearly this is, if this is a cover, then it's a cover of size k, right? So we have proved the entire thing. Then we are going to consider several things separately. So I'm going to first claim if I have a matched edge, then it's definitely covered because one of its endpoints is dark. Right? We only do a switching between dark and white if it is indeed if it's a matched edge itself. Right? So I only need to show that this thing doesn't happen. There is an edge that's unmatched, and two of its endpoints are both white. Okay, I'm going to first claim this node cannot have a matched edge. Because if it does, then this is alternating path, and I'm going to switch these two. Okay, makes sense? Okay, so this doesn't exist. So it can only have unmatched edge. Now, what can I say about this node? I claim this node needs at least one matched edge. Because if it doesn't, right, then I should add this guy into my matching. Right? It doesn't violate any constraint. Right? I didn't add that because there is probably a matched edge connecting to this guy. Then I'm going to, so then this guy has to be dark because this one is not. Right? Then how did this one become dark? It must come from some other guy on the left. Right? So there is an alternating path going back and forth. Something like this. Right? There is an alternating path starting from left, but ends here. Right? Because we showed that this guy is not connecting to any matched edges In that case, what I'm going to do is I'll match this edge, match this edge, match this edge, and unmatch these two edges. And that's a larger matching. So I removed the 2, I added 3. So that means max matching of K leads to minimum cover of K as well, which also means max flow of K in our network flow. Okay? So this part, this equivalence is not required. And you should know this proof, the proof of Edmond-Karp, and know that matching and cover can be solved by network flow, and that Dinich's name is spelled not as Dinich. Okay, that's everything for today.